So, all right. Okay, so what is the most simple, most basic problem that we can look at? It's written here. We only have, okay, let's start like this. No density variations, the same density everywhere. No friction, no Coriolis force, no influence by nonlinear terms. We come to that later on, what nonlinear means. Okay, so just one layer of fluid, and the only variable that you have is actually something we call dynamic pressure. The pressure gradient. Okay, it's a pressure gradient force. And this is added here on the right hand side of the equation. We have two momentum equations, one for U and one for W, and on the right hand side, activate the mouse. You can see here on the right hand side, this is the pressure gradient force. Okay, for U, in the U direction is the gradient in the X direction, and we have a pressure gradient in the vertical. When you think about dynamic pressure, and I urge you to read or study these parts in these books, is actually that here the gravity force does not come into play because the density is the same throughout the fluid. Inside this layer of fluid, there is no buoyancy force, so everything has the same density. The only effect that comes into play here is actually the slope of the sea surface, and that actually sets up the pressure gradient at the sea surface, which drives from the boundary, induces current. We'll illustrate that later. So these are the two momentum equations. And then we have a continuity equation. This is volume conservation. Again, you can think of little control volumes, and what it means is that the inflows and outflows of volume through any of the, in 2 dimensions, we only have 4 sides, have to be balanced, end up 0. This is what. Okay? So now if you vertically integrate, you get an equation for the free sea surface here, which is written above my head here. If you look at that, you can actually identify this. We had something like this on the shallow water equation. Okay, so this one is the rate of change of the sea level. And this follows on from a horizontal divergence of the volume transport. And what you have to do in this model is you actually really have to vertically integrate from the bottom to the top all the U components and derive the horizontal gradient. And then you can relate the sea level elevation. This either can be positive or negative. You can relate that to the surface pressure, surface pressure anomaly, and we call that a dynamic pressure. And it's just given here by this one. There's the acceleration due to gravity comes into. So now, what's the problem with these equations? It's a very, very basic problem. There's nothing much in there, but there's a big problem. Look at these equations. What are the unknowns? Okay. We have 3 equations, and we have 3 unknowns. The unknowns are U, W, and P. P is pressure. And 3 equations, but we don't have any equation for P. You see, the P is on the right-hand side. Pressure is on the right-hand side of 2 equations. And so this turns out to be very complex. We don't have an explicit equation for P, but now I'm going to tell you of how you can solve these. And it turns out to be a little bit complex anyway, but you only need to do it once, because once you have a model, you just need to apply it. You don't need to do that more than once. All right.